Okay, so we are going to start this student seminar. This time it's going to be Miss Astrid Blin, that she is going to talk about Introduction to Chiral Perturbation Theory and its application. So as all the time, she's trying to be as much academic as she can do, and we have to do a lot of questions because this is a kind of training for all of us. Please.
Thank you for introducing me. Hello. If I speak too low, please let me know, because I tend not to have a very strong voice. So as Roberto said, I'm a PhD student here. I'm Astrid, and I'm going to introduce you to Chiral Perturbation Theory, because that's the tool I use every day in my work. So before I speak about the applications I have in my projects, I will introduce you to the theory itself. So let's see if this works. Yeah. Okay, so why do we use chiral perturbation theory? So in principle, chiral perturbation theory is something that we use in an energy region that still belongs to high energy physics, so where usually perturbative QCD methods are used, but in the low regime of it, so where the perturbative QCD breaks down. In this case, effective field theories have to be used, of which one of them is chiral perturbation theory, which I will introduce in this talk. And after having introduced it, finally I will talk about two projects I'm mainly working at, which are Polarizabilities and photopion production, which I will introduce you to later. So when we're talking about strong interaction, or about interactions in general in physics, there are four. So the strong interaction, weak interaction, electromagnetic, and gravitational. The weak and electromagnetic interaction are many times put together as one theory of electroweak interaction, because as we can see here, at higher energies, those two theories actually can be combined into one and can be described with the same formulas, same expressions, because the coupling constant, so the strength of those interactions, is exactly the same. What one tries to do in physics is to actually unify all of the four interactions, so also the gravitational and strong interaction. The gravitational one we at the moment keep completely apart because the theories are completely different than the weak and electromagnetic one. The strong interaction, as you can see, almost can be combined with weak and electromagnetic interaction, but not quite. So actually it's at the moment, in the state-of-the-art physics, we cannot combine strong, weak, and electromagnetic interaction into one, which would be the grand unified theory. So, okay, I have to put this back. Good. So, as you can see, the electromagnetic interaction is actually the only one which grows stronger at higher energies, while the strong and the weak interaction goes weaker with higher energies. So why is that? This is a very simplified image of how it works. So it's not the complete description of it, but as you can imagine it. So if we look at electromagnetic interaction, it's actually quite intuitive that at higher energies, which also means smaller distances, that it will be stronger. Why is that? So if we have two charges, let's say for instance a proton and another proton, which are somehow distant in space, we will have photons that will travel among them. And the photons are the carriers of the electromagnetic interaction, and they themselves do not have a charge, so they're neutral. And as they're traveling in space, let's say in vacuum, they will not just be stable photons forever, so actually by the knowledge we have now, they constantly transform into virtual particles instantaneously. So a photon that travels in space will actually, for a small instant, transform into pairs of positrons and electrons, for instance, which will then recombine into photons again. So as the photon is neutral in total, when it's transforms in those pairs of particles, the two particles together have to be neutral as well. That's why we have positrons and electrons, so they cancel each other. And therefore, the particles that appear are charged themselves. And since now, as we had the beginning image of a proton on one side, another proton on the other side, and the photons traveling between them, there will be a cloud of positrons and electrons around those photons traveling in space. And this cloud of charged particles will actually screen off the effect of the initial protons that we were looking at. So that's how we imagine that if the distance is further, there will be more screening particles in the middle, and therefore the strength of the electromagnetic interaction grows weaker. This is very intuitive because as we know, if two charges are far away from each other, the strength they feel between each other will be smaller. So why is that not like this in the strong force? The strong force can equivalently be described as electromagnetic force, except that the photons are not, well, the carrier particles are not photons anymore, but gluons. Gluons also don't have a electromagnetic charge, so they're neutral in that sense, but they do have a charge of the strong interaction. So gluons carry the so-called color charge. And since they're charged themselves, when they also travel around in vacuum and form those pairs of virtual particles, they can actually transform into even more gluons. So the main difference is that while in electromagnetism we had a carrier of the interaction that was neutral, in the strong interaction we have a charge for the carrier of interaction, and therefore when it travels in space, it can potentiate itself, so we talk about an anti-screening effect, and the further two particles are from each other, the more potentiated the strength between them will get. So what we can imagine, for instance, are two quarks that are inside of a nucleon, for instance, so inside of a proton that is made out of three quarks. We can imagine that the gluons traveling between those two quarks will have this kind of fluctuations that they transform into even more gluons, and therefore if we try to separate the quarks, the strength between them will grow always stronger because there will be always more gluons popping up in the vacuum. And that's the reason why actually we talk about quark confinement, so we cannot find quarks isolated in space, because when they're too far from each other, the strength of the interaction will grow so big that it will pull them back together again. So what happens, as we saw in the diagram before, is that at higher energies, which is equivalent to small distances, the strong interaction gets weaker. And if we go further away, so at smaller energies, the strong interaction grows very high. And I'm always going the wrong direction? Okay. So then if we're in the high energy regime, so the small distances inside of a proton, for instance, we talk about the perturbative regime. Why is that so? So the strong coupling constant is so small that we can say, okay, it's much smaller than 1. And if we're, for instance, describing a particle in space, we can imagine it as this line being a quark traveling in time. And as I said, particles that travel around in vacuum usually have virtual fluctuations, so vacuum fluctuations. So this quark is not only itself, but can also decay into a pair of other quarks or gluons. So here we have like corrections of other particles, which are virtual particles. And this is the simplest correction to it, and we can go to always higher corrections, so adding more and more of those loops. And if we try to put in the theory now, actually for each of these vertices that are here, we have the strong coupling constant alpha s appearing once. So while in this diagram where we have the naked quark, let's say there is no vertex, so it's just a line, we have something that goes with alpha s to the 0. And in this diagram we already have something like alpha s to the square. And here we already have alpha s to the cube. So it's more or less like a Taylor development that we can do, where the first diagram is constant, and then the second diagram is already quadratically with the expansion parameter. And as with every good Taylor series, if the expansion parameter is small, which it is in this case because it's a strong coupling constant, it will grow smaller the higher the terms in the expansion series. So what we usually do in perturbative QCD is to take, let's say, only the first 2 terms, for instance, and then say, okay, the other terms are already much smaller, so they're only corrections to the initial theory, so we don't need to take them anymore, because of course we don't want to take all infinite terms, because we cannot calculate infinite things. And also they get more complicated in the calculation. As you can see, there are always more complicated structures appearing. And therefore we say we just stop the series where we see that it is already good enough to reproduce, for instance, what we are expecting from the experiment. But what is now the case at lower energy? So we're talking now about large distances. We're not inside of the proton or the neutron anymore. We're, for instance, talking about two protons interacting with each other inside of a nucleus of an atom, for instance. So there we're already talking about large distances, so it's actually still quite small, but large enough for the perturbative QCD not to work anymore. So what happens is that the strong coupling constant will now be much bigger than 1, and therefore if we try to do the same naive Taylor series, let's say, as before, the first term will be of a specific size, and then as we go to alpha s linear, it gets bigger, and alpha s to the squared gets even bigger. So it's a breakdown of perturbative theories, because actually the higher you get in the terms, the bigger the correction. So you cannot say you can stop at the specific order, because the other orders will give much more important corrections to the whole thing. So we need a different approach. We know now that it's not the strong coupling constant that is good to use for the expansion. We need something else to do an expansion in the theory. And there we go to effective field theories. Effective field theories are not pure theories as such that they can describe the physics just by using itself. Actually, what we need in the theory is also experimental input, but to this I will come later. So what we choose in the effective field theory are new parameters that are actually smaller than 1 and where we can do an expansion. And since we're talking about small energies, we can also say, okay, if the energies are small, the momenta of particles will be small, and we can choose particles that have a small mass. And we know that perturbational QCD breaks down around 1 GeV. So if we go to energies lower than 1 GeV, the perturbative QCD doesn't work anymore. And therefore we say, okay, this is our scale, and we want to make an expansion in parameters that are much smaller than this scale. And a case of that would be, for instance, pion masses. So pions are hadrons that are made out of 2 quarks. Because they have masses around 150 megaelectron volts. So if we actually take as an expansion parameter the pion mass over the scale, we already have a parameter that is 0.1 more or less. So if we make a Taylor series around that, we go to terms that are then 0.01, 0.001, and so on. So the corrections will be always smaller, and it's a good expansion parameter. The important thing here, and that's actually the main difference between the approach of using perturbative QCD and going to effective field theories, is that when using perturbative QCD, we're actually talking about quarks and gluons, so the things that happen inside of a nucleon, while in chiral perturbation theory, they're not the degrees of freedom anymore. Now we're actually not, we ignore that quarks and gluons exist. We just talk about mesons and baryons, that are the hadrons that are made out of quarks and gluons. So instead of really looking into the elementary particles, the quarks and gluons, we talk about protons and neutrons and pions, so the things that are made out of the elementary particles, and for a moment completely forget that those elementary particles exist, or actually even assume that protons and neutrons are elementary particles themselves. So here you can already see, of course, this is a theory that works at a specific range of energies, but will not work always. So it's an effective field theory to describe this region only. But before I go deeper into chiral perturbation theory itself, I want to introduce you to the symmetry which it is based on. So what we say is that all fermions, so all particles with spin 1/2, come in 2 versions. So one left and one right-handed version. That's actually where the name chiral comes from, because chiral in Greek means hand or handedness, I guess, and therefore we talk about the chiral symmetry. And we know that if those fermions don't have any mass, that the right-handed fields and the left-handed fields will decouple and can be treated completely differently, so they don't mix. How can we imagine that? That's again a simplified image. So if a particle is massless, it can in principle travel with the speed of light. So if its handedness, so the handedness explains how the spin is oriented versus the momentum of the particle. So if the momentum is, let's say, forward and the spin is backward, then it is left-handed, and right-handed for if they are parallel, really. So if a mass is traveling with the speed of light, then in any reference frame it will have the same handedness, because in any reference frame it will always have the same direction as the spin. If we now give a mass to that particle, it means that it's not traveling at the speed of light anymore, so we can find a reference frame that is actually faster than this particle. So if we choose a reference frame that is slower than the particle, the momentum will, for instance, go in front and the spin in front, and if the reference frame is faster than the particle itself, then it sees the momentum as if it were inverted. So the spin is still the same, but the momentum inverted, so the handedness of the particle in principle inverted. So if they're massless and they're originally right-handed, they will stay right-handed, but if they have a mass, the right-handed ones can transform into left-handed ones, so they're kind of mixing then. So we talk about the chiral limit, where the symmetry is absolute if the fermions are actually massless. But we know in nature quarks do have a mass, so it's rather small compared to, for instance, the scale we were talking about, the symmetry breaking scale. It was around 1000 megaelectron volt, but it exists. So it's not a pure chiral symmetry that happens in nature, it's a broken symmetry. But since the breaking is very small, so as I said, for instance, for up and down quarks, it's around 5 to 10 megaelectron volt, their mass. Since the breaking is very small, we can just introduce it by hand and pretend that it's like a correction to the symmetry. So the symmetry is not absolute, it has a small correction. The bigger problem is that, okay, for the up and down quarks, the breaking is very small, but for the things that are made out of the quarks, so pions, protons, and neutrons, the breaking is actually rather big, because the pions have masses around 150 megaelectron volt, while protons and neutrons have masses of actually the scale itself, so around 1000 megaelectron volt. So we cannot say, okay, we also explicitly break the symmetry by introducing those terms by hand. Because we would not just be breaking the symmetry, we would be destroying it completely, because the corrections would be, let's say, bigger than the theory itself. So we need something else to explain the whole situation. And in this case, we talk about spontaneous breaking of symmetry. So maybe you have already heard of the Mexican hat model. That is called like that because it looks like a Mexican hat. Maybe the Mexicans over there don't agree because they're laughing, but well. And so it's a simplified version to explain what spontaneous breaking of a symmetry is. So we can imagine that this is a potential, let's say gravitational potential, and we could place an object here in the middle of the peak. So let's say we place a ball on the top of the Mexican hat, and if it's in the middle of the hat, it will see the hat is completely symmetrical. So it looks to the left and to the right, and it sees exactly the same thing happening in both directions. But if we kind of put it out of its very labile equilibrium, so it's not a stable particle, it will immediately go into the valley of the hat, because that's where its minimal energy is. It will always try to go to its ground state, let's say. And if the ball is in the valley of the hat, then it will not see the symmetry anymore, because if it looks to this side, it will see the border of the hat, and if it looks to the other side, we'll see the middle of the hat. So suddenly the ball that is actually in a still symmetrical potential, because the hat didn't change, the ball will think it's not in a symmetry anymore. So that's what we talk about when we're speaking about the spontaneous break of a symmetry. So what happens is the potential is actually still symmetrical. We still have a symmetry, but it's hidden. So in the ground state of the situation we're describing, in this case the ball in the potential, in the hat potential, in the ground state, the symmetry will be hidden, but it will still be existent. So it's not like breaking the symmetry by introducing explicit corrections like it was with the slide before, with this explicit breaking of the symmetry. It's just hiding the symmetry, but it's still there. So in this case, actually, if we assume that the up and down quarks have masses around 5 megaelectron volt, and if we use the spontaneous breaking of the chiral symmetry now, which will be with a, let's say, potential like this, then actually we can make pions and protons and neutrons get the masses they have without completely destroying the symmetry, just by hiding the symmetry. So that's, of course, a simplified version of how a spontaneous breaking of a symmetry works, but it's just for you to have an idea that we're not saying that we destroy the symmetry, we're just hiding it, and it still works and describes nature. So now let's go back to chiral perturbation theory. So as I mentioned, we want to have an expansion in terms of small parameters, and the parameters we choose specifically in chiral perturbation theory are exactly small masses over a scale of masses which is around 1 GeV, and small momenta also. What we also want, since the underlying theory is a chiral symmetry, is that all terms we introduce in the theory are compatible with that symmetry. But if we're developing such a theory, we can start with the easiest terms that can appear, but we can always invent more complicated terms that are also compatible with the theory. So what happens in principle, again, we have infinite terms, and we don't want to calculate them all. So just like in perturbative QCD, we want to have an order where to stop, where we say, okay, this is enough to take these terms, and the other terms are not as relevant anymore. And in this case, since expansion parameters are masses over scale, we just say things that go linearly with this term, they are the first order of chiral perturbation theory, and if it goes to the square, it's the second order, and so on. So we order the terms that appear in the symmetry with orders of the pion mass over the scale. The problem is, since chiral perturbation theory is something that was invented, let's say, out of nothing, so it doesn't have underlying theory behind it, it's just a theory that works in this regime of energies, is that the higher we go in the order, the more unknown coefficients appear. So how can we imagine that? If we were talking about the Taylor expansion, the first term of the Taylor expansion, the one that goes linearly with the pion mass over lambda, it has a coefficient, let's say, A. And then the second term has a coefficient B, and so on. So those A, B, C, so the coefficients of the Taylor series, since the theory is invented at the moment, we don't know what those coefficients are. So we can think, okay, so the theory doesn't really help us because we're inventing something without knowing what the numerical values of it are. So what we actually have to do is we use the formula we invented for a theory, and then to actually make them usable, we have to go back to the experiments and fit those formula to data. And only by fitting the formula to data can we get information about the low energy constant, that's how the coefficients are called, to further be able to use them as a usable theory. Okay. What is also important, so when theoreticians of high energy particle physics are calculating their processes, many times the word renormalization appears. So what is that? The problem when we're calculating diagrams of specific processes is that usually infinities will appear in this form. So we have things that go with 1 over dimension minus 4. Since we're in Minkowski space, the dimension is 4, so we will have something like 1 over 0, which is an infinity. And in perturbative QCD, so at the very high energy range, the normal QCD, let's say, there are tricks to get rid of those infinities without saying, okay, we're cheating because we're just hiding infinities and they should be there in principle, but they're probably rather complicated. And the good thing about chiral perturbation theory is that it's actually easy to get rid of them. The thing is that, as I said, the coefficients of the chiral perturbation theory are unknown a priori. So we can say, okay, if they are unknown anyway, we can just take those infinities and put them inside the constants, because it's the same to say I have an unknown constant that is maybe 2, or I have an unknown constant that is maybe 2 plus an infinity, because I don't know them anyway. It sounds like cheating, but it's actually not that different than something you all assumed and accepted in school, which is, for instance, when calculating the potential energy of the gravitational field of the Earth. What you usually do is you take the formula m times g times h, so the mass of a particle times the gravitational acceleration times the height at which it is. And there's already the definition problem. We have the height, and how is the height defined? It can be the altitude calculated from the center of the Earth, or it can be from the sea level, or if we're talking about the top of a mountain, it can be the distance to the next tree, for instance. So we're actually, what we're doing is just saying, defining where the zero is. And if we define that the zero is where the sea level is, it's correct. We have a potential energy with a specific value. And if we define that the zero it's at the treetop, it's still correct. It's just a relative value that we get out of it. So the thing is exactly the same here. So what we're doing is just calculating relative values. So we're not getting an absolute value, but the relative distance between them. And we're just redefining where our zero is by introducing an infinity. We say that the zero is not anymore at 2, it's at infinite plus 2. So it's exactly the same, we just don't get absolute values, we get relative values that are always sufficient for physics to be able to describe what happens in the world. What we see in the experiment, therefore, is, for instance, the coupling constant that I here call, just as an example, g. And what will appear in the formulas is actually g minus infinity. But since infinity will not be used anymore, we just hide it inside of the g. So what we say is, okay, I have a formula where a g appears, which is actually a g minus infinity, but I know that later on in my calculation the infinity will appear, which will exactly cancel this infinity here, and therefore I will just have the naked value of g again. So I'm just shifting the definition of my coupling constant. Okay, so up to now what I said was that we're doing an expansion in pion masses. So the Chiral Perturbation Theory was originally introduced to describe the processes between mesons, so particles with 2 quarks, like pions, for instance. But okay, then we can calculate things like pion scattering, but actually there are many more interesting things that it cannot describe if we just use it for pions. So for instance, if we want to know the interaction between protons and neutrons, it would not be described in this theory. So what we want to do is to introduce baryons, which are, for instance, protons and neutrons that have 3 quarks, into the theory as well. The problem with introducing baryons is that they have higher masses. So as I said before, the pions have masses around 100 megaelectronvolt, while protons and neutrons will have mass around 1000 megaelectronvolt, which is actually already exactly the mass of the breaking of the perturbative regime that I was talking about, so 1 GeV. So if we introduce protons and neutrons in the theory, we have to be careful, because, for instance, if before we had terms that went with pion mass over the scale to the square, this would be rather small, because we would have 100 divided by 1000 to the square, so 0.01. And if we now go to the baryon sector, so introducing protons and neutrons, we then, instead of having the pion mass, we will have the nucleon mass. And here we would have something written like 1000 over 1000 to the square, so 1 to the square. What does this mean? That if we go to higher orders, we're actually not going smaller in the Taylor series, we're always keeping the same, because we're always going 1 and then 1 squared and 1 cubed, so actually the orders are basically all the same. That's of course a problem, because we want the expansion series to stop at some point. And therefore, when introducing baryons, we have to take special care about these kind of terms that appear. But it's already possible, so theories have been developed to also include protons and neutrons. And sometimes those terms appear, but again, we use the same trick that sounds a bit like cheating as before. We say we still don't know what our coefficients are, so these terms that appear that are power counting breaking terms, so that if we go to higher orders, they're still have the same importance as a lower order. We hide them in those coefficients and just redefine the zero again. So also in this case, it's rather easy to get rid of those complications. So Chiral perturbation theory has those two advantages. One is it's very easy to renormalize it, as opposed to perturbative QCD. We just hide away the infinities and act as if they didn't exist, and we just shifted our zero. And the problems with power counting, because introduction of protons and neutrons in the theory, can be gotten rid of in the same way. The disadvantage of the Chiral perturbation theory is actually the same. So why could we hide them away? Because we didn't know what those coefficients were, and that's exactly the problem of Chiral perturbation theory. We don't know what those coefficients are. So as I said, we need experimental data to fit the coefficients. And the thing is that this Chiral perturbation theory has already been used for decades, and experiments that underlie it or that are combined with it have also been done for decades. So at least for the first orders of the Chiral perturbation theory, we actually already know the constants that appear so well because of experimental data and many fits having been done, that we can use them without having to fit them anymore. The constants that appear at the lowest order are, for one, the weak pion decay rate. So the rate with which a pion will decay into a pair of an electron and neutrino, or a muon and a muon neutrino. And the other constant that appears is the actual vector coupling constant. So this can be taken out of beta decays of the protons. When these are established, which they are very well established by now, we can use them to predict other values. So now we can say we don't need the experiments anymore to fit our data. We can say we already know what our constants are, and we can use them to predict things that haven't been experimentally tested yet. The most famous example, and probably the first success of Chiral perturbation theory, is the Goldberger-Tryman relation. It is a relation between strong interaction and weak processes. What it says is we want to calculate the coupling constant of a nucleon to a pion. So if you are inside of an atom, for instance, you have like protons and neutrons, and between the protons and neutrons you have pions traveling around and interacting with them. So it's interesting to know, for instance, how strongly those pions couple to the nucleon. And this coupling I call G pi n. And by using Chiral perturbation theory, we could see that it's actually a very simple value that comes out. It depends on the mass of the nucleon, so of the proton or the neutron, on the Ga coupling constant I talked about before, and the F, so the weak pion decay constant that I also talked about before. And since Ga and F are experimentally well known, they can be assumed as constants that don't have to be fitted, and we actually have a real prediction of Chiral perturbation theory that says how strong a pion couples to a nucleon using only information about weak interactions, actually, because the beta decay which flows into the Ga is a weak interaction. This is a really a complete prediction, because here it's an absolute value. So I said before that many times you have to shift the zero. In this case, no infinities appear because we're only doing a calculation at tree level. Also, no power counting breaking terms appear, and therefore it's really a pure prediction, an absolute value, without having to consider where the zero is. So this was the first success of Chiral perturbation theory, because it predicted that the coupling value would be this one, and experimentally one can see that it's really so. The way around. Okay. As I said, that was a first success. Then we can use Chiral perturbation theory for many other things, and that's what I do in my projects. So one of my projects is calculating polarizabilities. What are polarizabilities? So if you have a non-elementary particle in an electromagnetic field, it will feel the strength of electromagnetic field and be stretched. It will suffer polarization in principle. How can we imagine this? Here is the example of a proton. A proton is made up of two up quarks and one down quark. The up quarks have a positive charge and the down quark has a negative charge, and therefore if we apply an electromagnetic field, the up quarks will be pulled to one side and the down quark will be pulled to the other side, and therefore the particle will be kind of stretched, one can imagine. And the strength with which it is stretched, so with which it is polarized, is polarizability. The higher the polarizability, the more the effect of this electromagnetic field on the particle. Since we're talking about electromagnetic fields, they are experimentally extracted via Compton scattering. The most famous example of Compton scattering is a photon scattering on an electron, but actually one can do Compton scattering on all types of charged particles. So for instance, one can do Compton scattering on a proton, which is exactly the same as with the electron. The photon comes in on the proton and rescatters away from the proton. I will never learn. Okay, so as I said, the Compton scattering happens on all charged particles. Then you could say, okay, but then we cannot get information about neutrons because neutrons are neutral. Yes, that's true in total, but also neutrons, they're not elementary, they're made out of quarks, and the quarks that are inside of the neutron, they do have a charge. So the photons that are doing Compton scattering will not do Compton scattering on the particle as a whole, but on its elementary structure, the down and the up quarks. So also the neutron has Compton scattering effects. Now I want to remind you that while in QCD, in perturbative QCD, in the high energy physics, we always talk about quarks and gluons as our fields. In Chiral Perturbation Theory, we completely forgot about the existence of quarks and gluons, and we spoke only about neutrons, protons, and pions, so the things that are made out of quarks and gluons. And therefore, if we're describing this situation of Compton scattering on a neutron with Chiral Perturbation Theory, we don't say the photon couples to the quarks. What we say is that, okay, the neutron has virtual fluctuations, so vacuum fluctuations, and for a moment it splits up into a proton and a pion, and then recombines into a neutron again. And while it's split up, the photon can couple to the pion, which is charged, or to the proton, which is also charged. So what happens is that we have the Compton scattering on the neutron described as the neutron splitting up into charged particles, the photon coupling to those two charged particles, and then everything recombining into the neutron again. So the difference between the situation of the neutron and the proton is that for the proton we could describe it as the photon coupling to the proton itself, so it was a first order calculation actually, and for the neutron we already need a loop correction, so say the neutron splits up into something and that's where the photon couples, so it's already a higher order calculation. And that's actually something that is a bit annoying about Chiral Perturbation Theory. While in QCD, many times it's enough to just take tree-level contributions, so lowest orders. In Chiral Perturbation Theory, usually we have to go to at least order 3 or something. So we have many corrections at higher orders that have to be calculated, which means that there is more calculation disaster going on here. The reason for that is that at the normal high energy QCD, the expansion parameter, which was a strong coupling constant, is very small. So if we go to higher orders, the corrections will be very small as well. While in Chiral Perturbation Theory, the expansion parameter was around 0.1. And therefore, if we're going to higher orders, the corrections will still be rather big. So 0.01 is still quite big compared to 0.1, for instance. So we need to take more orders into account until we're happy enough with the corrections. Yeah?
Here in this theory,
yeah,
that your photon has to, for the Compton scattering, that your photon has energies lower than the scale.
Yes, so the photon, in the case of Compton scattering, has energies around 100 to 100 mega electron volt. If it would have high energies, there would be other processes happening. So, for instance, if the photon goes in, it could just produce another particle or break up the particle or something. So the energy regime of Compton scattering is around 100 mega electron volt, and therefore that's the reason why we need Chiral Perturbation Theory, because the perturbative QCD methods wouldn't work anymore. thank you for reminding me of it. Also, in this case, just as the first example I gave you, we don't have any power counting or infinity problems, so the values we can calculate from polarizabilities are absolute, so no relative shifts or anything, so they're real predictions. So now again, for polarizabilities on protons and neutrons, there are many experiments that have already been done. And the only thing that we did by using Chiral Perturbation Theory was to test the theory. So we saw the same values came out as an experiment. Great. That's no new information. So what we want to do now is to extract things that are actual predictions, and we want to be faster than experimentalists in principle. So while protons and neutrons are very well studied with experiments, we want to think of particles that are not yet accessible via experiments, and those are, for instance, hyperons. What are hyperons? They're not that different than protons or neutrons, only that instead of being made up only of up and down quarks, they also have a strange quark inside. A strange quark is the next lightest quark after the up and down quark. It's in principle a bit like a down quark. It also has negative charge, but it's heavier. Since it's heavier, the particles that are made out of it, so the hyperons, they are not that stable. So they will immediately decay into the stable particles that are protons and neutrons. So when hyperons are produced, it's actually not possible to keep them alive long enough to make Compton scattering experiments on them. And therefore, since we cannot do experiments, the only way to access information about the polarizabilities is by using theory. So that's where the chiral perturbation theorists come in and say, hey, we can do predictions about this. Okay. And we have to be a bit careful, of course, because I said the strange quark is a bit heavier. While the up and down quarks had mass around 5 to 10 megaelectron-volt, the strange quark has masses of over 100 megaelectron-volt. So actually we're already having a bigger break of the chiral symmetry. But it's still small enough, so it's still much smaller than the scale that is 1000 megaelectron-volt. And therefore, if we take care and we don't just naively use it in exactly the same way as with up and down quarks, if we carefully extend the symmetry, it's still possible to include the strange quarks as well. So what we do is to extend the theory from protons and neutrons, which have zero strangeness, they have no strange quarks inside, to a theory that includes the protons and neutrons that have strange quarks inside. So the sigmas and lambdas are those that have one strange quark inside, and those chi's here are the ones that, no, xi's are the ones that have two strange quarks inside. And this I did in the project, and I gave predictions for the values of the polarizabilities of these hyperons. And let's see if in later experiments at some point we can confirm what we extracted from theory. Okay, another project I'm working on is photopion production. As the name says, it's the situation where a photon hits on a particle and a pion is produced. The channel I'm looking at is the photon going in a proton. Then instead of the Compton scattering where a photon came out again, the energy of the photon being used to produce a new particle, which will be a neutral pion. And here the idea is we have the experiments and we want to reproduce the cross sections of those experiments. Here it's more the preliminary phase of the use of chiral perturbation theory. We're not predicting new stuff, we're still adapting the chiral perturbation theory to the experiment and doing fits to try to make it always better to be usable in other situations. And what we do every day then is we have our experimental data, which are these red dots with error bars, and we want to take our theory and see if it really describes what the experiment does. And since we're lazy, we first start at the lowest order, so only 3-level contributions, let's say, so no loop corrections and so on. And we overlap it with what the experiment said, and we see, okay, the results are terrible. So it's not enough to actually stay with the first order. Here at low energies, so at the energy threshold regime where the pine is produced, it's more or less okay. And at high energies, around 200 megaelectronvolt, it's completely different. So it doesn't have anything to do with the experimental data. So we see, okay, we do have to include higher orders. And that's what we do next. So the calculations we did then were to go to the third order. So we took the second order and the third order. And we see, okay, the corrections are already much better looking. It's the blue curve here. We see that the low energies, it kind of overestimates what the experiment says, and at high energies, it underestimates it. How can we understand this? What we're doing is, at third order, we're fitting all the constants we don't know, as I said, and it looks for the best average fit. So at medium energies, it will be the best fit, and on the other energies, it will kind of shift around the best fit. So if at low energies it overestimates the fit, at high energies, to compensate, it has to underestimate it. And we see, okay, we're already more confident about our theory, but we're still not happy because it's still not going through the experimental data, so something is still going a bit wrong with it. So there are several possibilities. Either we go to even higher orders. Actually, some groups did it. They went to the fourth order, and they got some small corrections, but actually really small corrections, so it shifted a little bit more to the experimental values, but was still not overlapping them. And it's a whole bunch of work, because the higher the orders in chiral perturbation theory, the more calculations go inside, the more fitting constants, and really gets very out of hand. And so we thought, isn't there another possibility to make the results better? And we thought, maybe we're forgetting something, so some particle we should include, which we haven't included. And actually, when there are photon pion production experiments happening, there's one particle that appears many times, so it's very probable to appear, that we never considered in chiral perturbation theory before. So it's the so-called delta resonance. A delta particle is not that different from a proton. It also has the same valence quark constitution. The difference is that while a proton is a spin 1/2 particle, which can be explained by Dirac theories, the delta resonance, which is just the resonance of the proton, has a spin 3/2. And the theories to describe the 3/2 spin particles are so-called Raritas-Schwinger theories, and they're a bit more complicated than Dirac theories, so that's why a priori we don't include those resonances. But since it's the most obvious resonance actually to appear from the proton, it would be kind of stupid not to include it, because, well, we're kind of avoiding one part that definitely appears in the experiment. So we try to include them as well. And although it's a bit more complicated to include them than the normal spin 1/2 particles, it's probably still simpler in calculations than going to actual higher orders like the other groups did. And as we saw, when we just by including the delta resonances, suddenly we had those green curves going with the experiment, so suddenly we had the perfect fit for all points and energies. And yeah, that is what makes the physicist quite happy if the results are so good. And you might say, of course, you have better fits, because by including new particles, you were including new fitting constants. So the more fitting constants you have, the easier it is to get better results, because you can shift more parameters. But that's actually not true, because the delta resonance doesn't bring any new fitting constants in. So when not including the delta resonance, we had 3 fitting constants. When including the delta resonances, we still had 3 fitting constants. So the delta resonances come in with only known values. The only thing they do is to shift the theory by an absolute value, and not with constants that can be fitted. So actually we're quite confident that it's a good thing to bring them in, because we're not cheating in the way that we're bringing new fitting parameters in. We're just shifting the values to what is expected when you include the resonances, and actually you get a better result. So the idea is exactly this. You use chiral perturbation theory, and go to higher orders and include the parameters you need until you're happy enough with the experiment. And when you're happy enough that the results are corresponding to what you expect in experiments, that's when you say, okay, I can use the theory up to this order. I can take the constants that I fitted, and those constants that I fitted can be later on used on other processes which haven't been done experimentally at the moment. So what I've tried to explain to you in this talk was to say that when we have perturbative QCD at high energies, and if we go to lower energies, it breaks down. So we cannot do perturbational theory as such anymore because the strong coupling constant gets too big. And therefore we need other approaches, which are, for instance, lattice QCD. That's something completely different, but you might have heard of it. Or effective field theories, of which one of them is Chiral Perturbation Theory. And we take as new expansion parameter not anymore the strong coupling constant, but masses of pions over a scale, 1 GeV. And the main difference is, I want to stress it again, is that while in QCD you use quarks and gluons, in chiral perturbation theory you really use protons, neutrons, and pions, ignoring the existence of quarks and gluons. And then you expand the theory, and for each order of expansions, unknown constants appear, a priori unknown constants. Those constants are then determined by fitting the theory to data. And then later on, when we're happy enough with the fits, we use the values we discovered for the constants to make predictions for processes that are not yet found out by experiment, and that we hope that maybe at some point in the future can be found out, but at the moment you can only do theoretical predictions of. So if you have any questions.
When you have the pion production, I mean, because all this theory is for low energy.
Yep.
In fact, this
pion production is also low. It's 100 to 200 mega electron volts. So
but more of that is just also the comment that in fact this process is very common in ultra high energy cosmic rays. This is the process that stop ultra high energy protons with the symmetry. So at the end is very low energy, but high energy.
In high energy processes, yeah.
But this stuff is still, I mean, all the time you have this limit of MEVs for the photon, but when you start to go higher, can you still be predictable, or?
No, so there is a scale where
point in which both theories don't mismatch.
So as far as I know, so if you go to much higher than those 200 mega electron volt, which is actually higher range of the experiments we fitted the data to, the chiral perturbation theory does not work so well anymore. And I think between the region, let's say 500 and 1000 mega electron volt, there is still not the combined theory that can overlap the two theories, as far as I know. So it's still that you have perturbative QCD on one side, you have chiral perturbation theory for the lower energies, but you have a range where there'll be dragons, so you don't really know how to explain it. That's the whole idea of the perturbative theories, that it's not the theory as such, you're actually expanding the theory to fit it to the region that you can look at, but it's not a full theory, so you can't solve QCD entirely, you can only solve it as expansion corresponding to energies.
That was the question. There's going to be a range in which perturbative QCD doesn't work,
and chiral perturbation theory
works. So, but
but also but
something that range to try to.
Say again.
Are some experimental results in the range in which both
that would
work?
At least not that I worked on. I don't know if people tried to go to 500 mega electron volt for chiral perturbation theory, for instance. But actually, chiral perturbation theory is already the theory that one introduces to overbridge the energy range that you don't know, because QCD is for high energies, and for low energies you have many descriptions as well. It's just a day-to-day life, let's say. And the range that we didn't know was exactly the range that is more or less covered by chiral perturbation theory. So it is already the bridging part. But one has to be very careful. There are, as I said, around 100, 200 megaelectron volt, it works very fine. And then if you go to high energies, usually it breaks down. So there is one part that is still not very kosher. Yeah. Was that your question? Yeah. Okay. Good.
No questions? No.
Yep.
And how do you get the Feynman rules if you have an effective Lagrangian? You can have the Feynman rules on the effective Lagrangian.
Yes.
But then your extra parameter that you said, that if you go up
Mm-hmm.
expansion.
Yep. Okay, so actually in the Feynman rule you always will have that constant that you don't know. And when you're then using the Feynman rule, the constant that you don't know will flow into the theory, and that's where you have to fit. So you have Feynman rules that are not absolute values like 1/2, 3/2 for the different isospin channels, but they are 1/2 times GA, for instance, or 1/2 times coupling constant C6. Those, yeah. So you have a Feynman rule with an unknown constant inside of it. Yeah. Does that answer your question?
And when you do the effective Lagrangian,
Yep.
you put all your parameters there. And
Yes. Mm-hmm.
by saying that you have this parameter will be smaller than 1, small, let's say, as a
Yeah.
parameter, then you make the series expansion, and then you get the parameters.
So,
The usual way.
yeah.
But then
Yep.
you don't get how you get the extra parameters. If you write the effective Lagrangian 3 parameters, for instance,
Mm-hmm.
maybe let's say 3 parameters, the mass of the particle over lambda plus
Yep. Okay. Mm-hmm.
the particle. Then you say the expansion is will be from mass of the particle over lambda. Then you do the series expansion over these parameters, and there will be 1, then the square, then the third.
Okay, that's not how you construct Lagrangian chiral perturbation theory. So what you do is to, as I said, the chiral symmetry is the one that it bases on, and what you do is construct something with a nucleon, a spinner of a nucleon, for instance, and a pion and another nucleon, and then you don't expand that what you constructed. You just say, okay, this is the simplest term you have, times a constant. And then when you go to another order, you're going, for instance, to include 2 pions between the spinners, and there you have a completely different constant that doesn't have anything to do with the original one. So it's not that you make a series, like a pure Taylor series or something, to construct the effective Lagrangian. You actually just think of all possible terms that are acceptable for the chiral symmetry, and then you put constants near those terms. And depending on the size of the constants, or depending on if there is a pion mass inside or not, that's how you order them then afterwards. But it's not the other way around, that you first expand and then those constants appear to the square or to the cube or so on. So you just kind of invent terms that are compatible with the symmetry and then put constants near them. Yeah. Other questions?
Other questions?
Okay.
If not, we thank Astrid. And the next seminar is going to be 19th of February with Evelyn. We're going to talk about electron flavor violation.
So